In this video, we're going to look at compound interest and the number e. In particular, we're going to use the compound interest formula to solve basic compound interest problems. We're going to develop the number e, and we're going to use the number e to solve continuously compounded interest problems. We'll start by discussing the infamous compound interest formula given at the top of the screen. A of t equals p times 1 plus r over n, all raised to the n times t power. We're thinking of this as a function of t, and notice that t is in the exponent of our expression defining our function, and therefore this is an exponential function. The variables and what they stand for are all indicated here. A of t is the account balance at time t. T is, of course, the time given in years. P is the principal or present value, which is essentially just the starting amount for either our loan or our savings account or investment. R is the annual interest rate, written as a decimal, and N is the number of compounding periods per year. And so in any kind of compound interest problem, we'll need to know several of these different variables and typically be asked to find the remaining one. Most of these values will simply be given to us. For example, we might be told that we are to deposit $500, and if that's the case, then that tells us that P, the principal or present value, is $500. The only one of these that sometimes can be confusing is the number n, the number of compounding periods, because we're not usually told directly this, but rather we're told indirectly how to find this. And there's some keywords to know to recognize when we're talking about the number of compounding periods per year. So if compound interest is compounded annually, that means once a year, semi-annually, twice a year, quarterly, every 3 months or 4 times a year, monthly is 12 times a year for 12 months in the year, and daily is 365 times a year, once each day. These are the most common frequency for compounding periods, although there could be others. But these 5 words do translate to these 5 particular values of n, shown here. So for a quick example of using the compound interest formula, let's consider this. So here we're asked that if we invest $3,000 in an investment account paying 3% interest compounded quarterly, we'd like to know how much the account will be worth in 10 years. So we see here that the principal or the depositing amount will be $3,000. We're told the interest rate is 3%, so as a decimal, that is 0.03. The interest is compounded quarterly, that is n equals 4 times a year. And we want the balance after 10 years. So we want t to be 10. And so if we take our compound interest formula, A of t equals p 1 plus r over n to the n times t, we can substitute all of our values into this equation. So we get A of 10 will be 3,000 times 1 plus 0.03 divided by 4, all raised to the 4 times 10 power. Of course, that exponent is 40. And this we can just substitute, we can just type this all into a calculator, and this will give us approximately $4,045.05. This is the value you would get when you round to the nearest cent if you type all of this expression into the calculator directly. If you approximate things along the way, you might be a little off. So it is a best practice to wait until the very end of the problem and type one single expression into a calculator. If you don't do that, you'll have more of an error, and depending on how accurate you're hoping the calculation to be, it might be too much error to count as accurate. As a second example, Lily wants to set up a college savings plan for her new granddaughter and wants the account to grow to $40,000 over 18 years. The account will earn 6% interest compounded semi-annually, and we want to find to the nearest dollar the amount that Lily needs to invest in the account now. This example differs from the previous example in which we were given the initial deposit amount and wanted the amount in the future. Here, we're given the amount we want in the future, $40,000, and want to know the necessary investment that we need to make now to achieve this. And so what we have is, in this case, we have the value of A to be $40,000. We have a time T of 18 years. We have an interest rate of 6% or 0.06 as a decimal. And it's compounded semi-annually, which means twice a year. So again, we can start with our compound interest formula and substitute in all of our given values. In this case, the A value on the left-hand side is 40,000. Our P is unknown. That's the value that we're trying to solve for. And everything else is what we were given. 1 plus 0.06 over 2 times 2 raised to the 2 times 18 power. So raised to the 16th power. So we end up with 40,000 equals P. This quantity in parentheses, 1 plus 0.06 over 2, ends up being 0.03. And of course, as we just said, 2 times 18 is 36. So if we divide both sides by 1.03 to the 36th power, we see that our principal is going to be 40,000 divided by 1.03 to the 36th power. And using a calculator and rounding to the nearest dollar, we see this is approximately $13,801. And so this is the amount that Lily would need to deposit today in order to guarantee there'll be $40,000 in this account 18 years from now, given the information about the interest that we were provided. Well, compound interest is not one of the most exciting topics there is in mathematics. It does give us a way to develop and explain one really important number that shows up over and over again throughout different areas of math, and that is the number E. So suppose that we do this completely absurd thing, and we invest $1 at 100% interest for 1 year. What we're really doing here in the compound interest formula is we're setting P, R, and T all equal to 1, and the 100% interest gives us the 1 for R. Now, while this is completely absurd, especially the 100% interest part, we can use the compound interest formula to compute the amount of interest we would earn on this investment at different compounding frequencies. So here is the value of this investment at all of these various frequencies: annually, semi-annually, quarterly, monthly, daily, hourly, every minute, and every second of that 1 year. The middle column in blue would be the formula. Notice that again, P, R, and T are all 1 in all of these formulas. That's our base investment values that we're given. And N becomes 1, 2, 4, 12, 365, 8,760, 525,600, and 31,536,000 respectively. If you evaluate the blue expressions using a calculator, you'll obtain the red values over on the right-hand column. And you'll see as these values increase, they start around $2, but then even with interest being compounded every second, we see that we still get around 2.71 cents or $2.71. We've extended it out, and we've seen the last couple here are all 2.718. And so it seems that as the frequency increases, as the value of N gets larger and larger, it looks like these values of our account balance get closer and closer to some number that's 2.718 approximately. And that actually is the number that we call E. So formally, we're going to define E to be the number that 1 plus 1 over N, all raised to the nth power, approaches as N increases without bound. This means that if we take n to be bigger and bigger values, e is the number that this expression will get closer and closer to. The table that we just looked at showed that there seemed to be a number that had this property, and so we're just giving that number a name and calling it e. And as we saw in the previous table, e is approximately 2.718282. However, it is an irrational number, which means this is about as good as we can do. Of course, we could use more decimal places in this approximation, but we're never going to be able to write down all of the digits after the decimal point, and we're never going to be able to write it as a fraction, at least as exactly as a fraction. Of course, we could approximate it in that way, but this is as good enough for our purposes that we need to know that e is approximately 2.7 or 2.71, depending on how accurate you'd like to be. It turns out that this number e can be used to model all sorts of real-life phenomena and is one of the most important numbers in all of mathematics. One basic use of the number e related to what we're discussing now is the continuously compounded interest formula, which is a of t equals p times e raised to the rt power. Here a, p, r, and t all represent the same quantities that they represented in the compound interest formula, and e represents this natural exponential number e that we just discussed, approximately 2.718282. Any scientific or graphing calculator should have a button on it that will allow you to represent e, and so you don't need to use an approximation for it. You can just use the calculator's button for e directly. So for a quick example, using the continuously compounded interest formula, let's consider a person who invested $1,000 in an account earning 10% interest per year, compounded continuously. And we want to know how much would be in the account at the end of 1 year. So we are here given a principal of $1,000. That's the amount being invested. An interest rate of 10%, 0.1. It is compounded continuously, so there is no n in this formula. We're going to use the formula involving e. And our value of t here will be 1 because we want the account balance at the end of 1 year. So our continuously compounded interest formula, a of t, is going to be pe to the rt. And we can simply substitute in all of these values. So we want a of 1 here, and that will be 1,000 times e to the 0.1 times 1. Of course, that exponent is just going to be 0.1. And so we can take this 1,000 e to the 0.1, evaluate it in a calculator, and we see that this account should have approximately $1,105.17 in it after that 1 year.